Hello everyone, today I'll be making a video about the second derivative, and in particular how you can use it to demonstrate concavity and find out whether a point is a local maximum or a local minimum point on a cubic graph. So let's start by drawing a function f of x, just a cubic f of x, and it'll look something like that, where you have one part that, where you'll have one part that's going up and then one part that's going down, and then it'll go back up again. It's like a little roller coaster. It'll go like wee, right? And here it's pretty obvious that in this f of x, you can see a maximum point over here and a minimum point over here. These are instantaneous, right? You go up, and then for an infinitely small amount of time, you're at a place of stop, and then you start going down again. That's why we call it instantaneous. And then you can also see that these are concave up, and then this is concave down over there, right? Now, if you know anything about the first derivative, you know that when the first derivative, f prime x, equals 0, the tangent to the line is horizontal, right? You're not going up or you're going down. You're just, staying there. So let's actually just draw in what the derivative, the first derivative of f of x would look like. So f prime x looks something like that, and I'm decently happy with that. It's not going to be accurate, but it looks pretty good. Yeah, so here I've drawn in f prime x, or the derivative of f of x, and it approximately cuts the x-axis where you see the local maximum and local minimum of the function f of x. So let's write f prime x here. And as you can see, when f prime x equals 0, you have your local maximum and your local minimum points. And we can actually understand that on a deeper level. So when the slope equals to 0, the tangent to the line, the first derivative, will look something like that. It's not a straight line. Hold on. It'll look something like that. That's better. And then at the local minimum, it'll look something like that as well, because it's instantaneous. As I said, you're going up and then you stop for like an infinitely small amount of time, and then you go down again. Same with the bottom part, you're going down and then you stop at the minimum and then you go right back up. Those are what minimum and maximum points are. So we can say that dy over dx over here equals to 0, and then over here dy over dx also equals to 0. And I hope that makes sense, because that's very important. Actually, let me move this little dy over dx equals 0 up here so we have more space. Right, so now that you have differentiated the function once, you know that there are one maximum point and one minimum point. If you actually differentiate some cubic graph, you'll find two solutions, right? Because a cubic, when you drop the power by 1, it becomes a quadratic, and then when you drop the quadratic by 1, you get a linear function. Okay, and drawing both of the graphs, both of the lines on the same graph, really helps to solidify this understanding. So now you can see f of x and f prime x over here. Now, we need to use concavity to find out which is which, right? And the way I'm going to do this is by highlighting the part of the cubic graph where the cubic graph's rate is decreasing, and then where it's starting to increase again. So the positive portion, actually. The positive portion is going to be in green, and then over here, it's also green up here again, because f prime x is positive here, and then in red, I'll just color the negative portion in. Something like that. There we go. So now we have the positive and the negative portion of f prime x highlighted, and as you can see, that matches up here. Here you have the negative portion, and then if we make this green, you have the positive portion, right? You have the negative portion, and then you have the positive portion. And then another interesting little feature, which I will briefly talk about, is the point of inflection. And that's where the rate, quote unquote, will start increasing. And I'll demonstrate this more later. It's going to be somewhere around there. Hold on, let me use green. And then here at the minimum point of the parabola of f prime x, your differentiated function, the first derivative, that will be the point of inflection. And that basically means that the rate starts to increase again. Now, I've been throwing this word around, rate, a lot. And let's actually tie it to the second derivative. So if we just differentiate f prime x again, without really knowing what happens. Let's differentiate f prime x when f prime x equals 0. So when f prime x equals 0, these are these little green points over here, like over here. And if we differentiate it, I'll draw it in orange. Basically, we draw a tangent to find out the slope of that parabola. We have a tangent line here. Sorry, that's terrible. Tangent line here, kind of like there, and then a tangent line there. Long tangent line. It doesn't even touch, whatever. It doesn't even matter, honestly, for our diagram. What's important is that you can see the kind of the slope of the tangent line, right? And let's make that black again. So this orange line over here is f double prime x, or the second derivative, f double prime x. And both of those are f double prime x. So let's just look visually at what's going on at these roots of the first derivative, right? The tangent looks like it's going down, and that makes sense, right? When the slope of the second derivative is negative, okay, so dy dx, when this is negative dy, then that means you're at the local maximum, okay? Now over here, the slope of that tangent line, the orange line, the second derivative, this tangent line is the second derivative, by the way, is positive, right? And so you'll have a dy and you'll have a dx over here, right? Right here you have a negative dy over dx, and you have a positive dy over dx when you're differentiating f prime x. And what this is the second derivative. So now, without further understanding, let's just establish that when f prime x equals 0, you're at either a local maximum or a local minimum point, right? And then if f double prime x, when f prime x equals 0, f double prime x is less than 0, so you have a downward sloping line, that means you're at the local maximum. And when f double prime x of that line when it equals 0 is positive, right? It's greater than 0, you're at a local minimum. Okay, and that makes a lot of sense, right? And why does that make sense? The second derivative talks about rate, and that's something I already brought up, right? Here you can see the rate decreasing. You're going up, 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 and then it's slowing down. It's slowing down, right? And when it's slowing down, when the rate is decreasing, I'm use green for that, you're going to see that the second derivative is less than 0. And here the rate is increasing. You're going on this exponential run. You're going boom, and then you're going all the way back up, right? So here the rate is increasing. And when the rate is increasing, the second derivative is going to be positive, and then it'll be more positive, and then it'll be even more positive. It'll just be even more positive. The second derivative will just keep on shooting right up. And now I think you understand that when you have a graph that looks like that, and it's like kind of concave, what we call concave down, the rate is decreasing, therefore the second derivative is less than 0, therefore that point is the local maximum. When it's concave up, when the second derivative is greater than 0, then you're going to have a local minimum point. And then I'll briefly talk about the point of inflection, because I think it's kind of relevant. Point of inflection is where you go from a decreasing rate, it just keeps on decreasing, and then suddenly you start increasing your rate again. You go from like, boom, your decreasing rate, and then you increase your rate again. And then you start to have a positive second derivative again, okay? And to drive this concept home about rates, right, I keep on talking about rates. Let me draw a few graphs. And I'll draw, let's say, this is f of x, and let's look at whether or not the first derivative is positive and whether or not the second derivative is positive. So the first derivative tells us the slope of the line. So f prime x is positive. Now f double prime x, the second derivative, tells us that the change of rate, which is the change of the first derivative, is 0, because the rate is not changing. If it's a linear line, if it's straight, that means your rate is constant, right? Okay, and then we'll have another graph here, a little bit. Let's inspect whether or not we have a positive second derivative. And we actually do have a positive second derivative here because the rate is increasing. Our first derivative is still positive. Our slope here is positive. If we differentiated that, we would find that we have a positive slope. Now, the third graph is interesting because, I won't try to like snap those into straight lines, because we have a positive first derivative, right, f of x. If you take tangent to that line and then find the slope, you'll find that that tangent is positive. It's going upwards, right? So your slope is positive. But your second derivative here is negative. Why is it negative? Because as we saw here, the rate is decreasing. You're decreasing in rate, therefore you're approaching a maximum. And for example, if we extended this, it'd go back down maybe, and you would hit your local maximum. Now, what about some downward sloping graphs? Here, same thing. You have a negative first derivative, but your second derivative is 0 because it's linear, it's constant, no rate change here. Again, let's do another graph. If you have something like that, you can see your rate is about to increase. Yes, your first derivative is negative, so f prime x is negative, is actually positive because the rate is increasing, right? It's all about the change of rate. Last one here, you have a negative first derivative, right? It's a downward sloping graph, but f double prime x, your second derivative, is also negative because the rate is decreasing. Okay, so I hope that made sense. This understanding of plotting two lines on the same graph really helps you to understand what's going on with the first derivative and what's going on with the second derivative, and it drives home the idea of concavity. So I really hope that helped. I mean, I love making this video because it's my passionate subject right now.